Welcome everyone. I'm happy that you made it to this morning session on the last day of the conference to hear about a new method that is probably going to revolutionize the way we are searching for black holes and neutron stars using microlensing. And this technique is called the dual field interferometry. My work would not be possible without my wonderful collaborators, including Subodong from Peking University and Antoine Marant from the European Southern Observatory. I'm pretty sure that most of you have seen this picture, which shows the distribution of masses of known stellar remnants, stellar mass black holes, and neutron stars. Many of these objects have been discovered by gravitational wave detectors, like Virgo, and they are shown here in blue. But there is also a smaller but still substantial population of black holes and neutron stars detected by more traditional electromagnetic observations. This plot has several very interesting features, but one of them is the fact that the masses of black holes detected by gravitational waves seem to be on average a few times higher than the masses of black holes that were known previously from observations in the Milky Way. This doesn't have a clear explanation still, and I think that trying to understand this picture, this distribution, is one of the biggest problems of the modern astronomy. Of course, we will not understand the population of black holes detected by Virgo if we don't understand the population of black holes and neutron stars in our own Milky Way, and we are still far away from that goal. Of course, gravitational microlensing has a great potential to discover dark objects, including black holes and neutron stars. In fact, about 1% of all microlensing events is expected to be by stellar mass black holes. So, over the 3 decades of microlensing surveys, we have detected about 30,000 microlensing events. So we should have about 300 black holes, but we only have one confirmed candidate. So why is that? Of course, the problem is that mass measurements in gravitational microlensing require measurements of 2 quantities: the microlensing parallax, which can be measured from the light curve of the event. For example, distortion of the light curve due to motion of the Earth around the Sun. But they also require measurements of the angular Einstein radius, which are much more difficult, especially for the dark lenses, such as black holes or neutron stars. There are basically 2 ways you can measure these quantities. You can either use astrometric techniques, and we will have the next few talks about that topic. Alternatively, you can use interferometers such as gravity, and this is what this talk is going to be about. As you know, during single-line, single-source microlensing events, usually 2 images of the source star are created. They are separated by roughly 2 Einstein radii. So this is angular separation of just a few milliarc seconds. This separation is too small to be resolved by modern telescopes, and to resolve such close objects, such close images, you need interferometers with long baselines. I would like to also remind you that interferometry is very different from the traditional imaging techniques that we are using in microlensing. So you need at least 2 telescopes that are looking at the same object in the sky, and then the light from the 2 telescopes is physically combined together to create fringes. And you are studying the fringe pattern to infer the parameters of the microlensing event. For example, you can measure the separation between the 2 images, which gives you immediately the Einstein radius. You can measure the position angle of the images in the sky, which gives you one-dimensional parallax information. And also you can measure the contrast ratio between the images, which again gives you some cross-checks against the light curve model. We are using gravity, which is, I would say, the state-of-the-art instrument used in the optical interferometry. Gravity combines the light from 4 8-meter VLT telescopes. These are one of the largest telescopes in the world, of course, located at Przemek Mroz Observatory in Chile. Because the separation between the telescopes is on the order of 100 meters, this allows you to resolve objects that are as close as 2 milliarc seconds away from each other. And although we are using the largest telescopes, one of the largest telescopes in the world, gravity is able to observe only relatively bright targets, like brighter than 9 to 10 magnitudes in the K-band. As you probably know, microlensing events that are that bright are very rare. So basically, we had only a few chances to use interferometers, such as gravity, to study microlensing events. These are the first two detections, the Kojima event from the 2017 and the Gaussian 19 BLD event. Both of these were unusually bright, which made these observations possible. In both cases, we were able to measure the Einstein radius with a very high precision, and also the masses with similarly high precision. Very recently, our group published the analysis of another very bright microlensing event called Assassin 2280. This was the first binary lens microlensing event resolved with gravity. Actually, in this case, we didn't have like point-like images, but the images were arc-like. They had arc shapes. Nevertheless, we were able to measure the Einstein radius and the masses of the both components of the binary very precisely. All of these three detections were possible because our targets were really bright, unusually bright. And this is because in the standard or on-axis gravity mode, we require a science target to be brighter than 10 magnitudes in the K-band, but there also has to be some adaptive optic stars nearby within 30 arc seconds of the event. However, in the recent months, there was a new mode of observations of gravity deployed. This mode is called the dual field wide mode. In this observing mode, you can observe much fainter targets, brighter than 14, 15 magnitudes in the K-band, provided that you have a bright reference star within 30 arc seconds of the microlensing event. So, as you know, because we are observing toward the galactic bulge, there are plenty of bright stars, and so the chances that we will have a suitable bright star within 30 arc seconds of our microlensing event is very high. So this increases the number of microlensing events dramatically that we can follow up with gravity. So this plot shows the cumulative number of microlensing events with timescales longer than 50 days as a function of the peak K-band magnitude. These are events from 2023. So as you can see, like underwhelmingly, we have maybe one or two sufficiently bright events that we can study with the normal gravity on-axis mode. However, if we consider microlensing events that have reference star within 30 arc seconds that is brighter than 10 magnitudes of the K-band, then the number of microlensing events that we can observe is growing by 2 orders of magnitude. And in my opinion, this is like a revolution that we waited for a long time. If you do some simulations, you can find out that every month, every VLT observing ground, you can observe as many as a dozen of microlensing events now. This new observing mode was made publicly available a few months ago in 2023. So our group put in several microlensing targets. One of them was August 2023 Belch 61. This is a fairly long time scale microlensing event with a time scale of 90 days. Here you can see its light curve. We observed it with gravity wide mode twice. One observation was before the peak, the other was taken roughly 2 months after the peak of the microlensing event. In both cases, we were able to see the fringes. So based on that, we were able to resolve the microlensing images. We are able to model the fringes. And from that, these are our measurements. And from that, we could infer the Einstein radius, the mass of the lens, the distance to the lens. We could also infer the trajectory of the source star in the sky. I would like to point out these are very precise measurements. So the Einstein radius is measured with precision better than 1%. The mass of the lens, its distance, is measured with a precision of a few percent. This is limited by the accuracy of parallax measurements, actually. In this case, the lens star is just mundane, a main sequence star, perhaps a white dwarf, but nevertheless, we are very happy with this result because it demonstrates that the new instrument is working as expected, and it gives us like good information for the future. Currently, we don't have any more observations because the VLTI, very large interferometer, very large size of interferometer is undergoing upgrades to its adaptive optics system, so the instrument is not available. However, these changes, when completed, will allow us to go even deeper than currently, and we estimate that we should be able to observe as many as 60 to 70% of all microlensing events in the galactic center with the all upgrades finished. I would like to also point out that these observations are really efficient. So we need just one exposure, 1 hour of observing time to resolve the images to measure the Einstein radius. So this is in contrast to the more traditional astrometric techniques in which you have observed your microlensing events for several years. Here you have an answer immediately. So we hope that these changes will make it possible for us to conduct like industrial scale searches for neutron stars and black holes in the Milky Way in the near future. Thank you.
When are those upgrades to the VLTI system going to be completed?
It's going to be completed this year.
Before the end of the ball season?
Hopefully, yes. We hope to get some commissioning data on some microlensing targets.
Very fantastic projects. My question is, if you go to such a many candidates, you can observe, is there any program on the blending?
Well, as long as the blend is separated by more than 1-2 milliarcseconds, then you should be able to separate it out. So actually, you should be able to see, I mean, you should be able to detect another object within a few milliarcseconds of the target. So in principle, you can like you can blend it.
Every time you can unmute yourself.
Okay. Hello. I have a quick question. You said that in the future there will be about 70% bulge macro event can be observed by VLT gravity plus. So, but the question is how to get the hundreds or thousands of VLT time in the future.
Yes, that's a challenge. One of the problems is that we are competing against the galactic center group, which is like taking observations of the Sagittarius A star. So you have to compete for the observing time. But I think the science case is strong enough to justify our request.
Simply the top question, you mentioned you only need one epoch, but you may have blending from the luminous lens. Do you need 2 epochs to resolve that?
That is true that we can have some blending from luminous lens. Of course, if we had 2 epochs or more, that would be we would have more information that would help us to disentangle these. But even with 1 epoch, we should be able to see the luminous lens. Of course, we can like revisit the event once the source returns to baseline, because then the contrast ratio between the lens and the source would be smaller, and it should be easier to see the lens.
I mean, if you want to industrial scale of neutron stars and black holes, do you have some pre-selection of candidates?
Yes, actually, it's like quite complicated, complex process. So VLTI runs are organized every month, so we select targets at about 1 week in advance. We look at long-time microlensing events that show little evidence for blending, and for which the microlensing parallax signal is consistent with zero, because we are looking for black holes, of course. But we also consider the facts, the other facts that the brightness of free-striking stars, the brightness of Leo stars. So there are like a lot of factors that can influence our choice. But we have developed a procedure for that over the past 2 years.
So just wondering, I mean, if you're in a situation where 70% of all microlensing events are targetable, then you can almost get away from having to select, right? You're almost kind of in a situation where you can pick a patch of sky and just try and monitor as large an area. So I'm wondering if you've got a kind of an optimistic level of VLT, realistic, but on the optimistic end of realistic, what kind of area could you actually cover?
Well, I think you can observe realistically, if we have enough time, every time, I think 1 night per month is enough. So 1 night per month is enough. So you should get 8 to 10 microlensing observations. I would also say that like people are thinking about expanding the VLTI, and there's some thought process at ESO and some other places to maybe build another telescope to make the interferometer larger, or to build actually a new thing. So it's something that people are thinking for the next decades.